I want to thank the organizers for allowing me to speak in this wonderful conference. I always learn a lot of the talks and the debates. So I will speak today about how to construct, or how are the essentials of the global states that one can, and algebras that one can define in collections of random variables, and then describe some features of it. And suppose that you start with a probabilistic system that to fix ideas, you can think of an atom, but it could be more general, whatever you want. But when you perform an experiment, if you want to speak about a probabilistic experiment, you need to speak about outcomes. I put 3 outcomes here, but this consideration applies for any number of outcomes. Then out of the outcomes, you can form an outcome set, and out of this outcome set, you can form a sort of event algebra. And in this algebra, you define probabilities that are expressed or condensed by the simple rules of Kolmogorov's actions. So when you have an experiment, you can describe it in a minimal mathematical way as a triplet, which is a measurable space. And what is important for us here is that sigma, the algebra of events, is a sigma algebra, and we can consider it a Boolean algebra. So Boolean algebras will be important in this talk. Random variables are defined as measurable functions. Once you have a measurable space, you can define very quickly the notion of a measurable function. And then you can also perform, of course, other experiments of a different type, and some of them can be performed together, but some of them cannot, and so on. We have relations of compatibility between experiments, and then you end up in something like this. For each copy of the system, you can prepare this line here as an experiment, this line. This is very similar to Edibot's notation, but I am putting pictures here to emphasize the fact that this is something that appears already at the phenomenological level, and with a very minimal mathematical structure, which are essentially the conditions of possibility of considering an empirical setup in a probabilistic way. So of course, this is the same, but with the random variables. Now we have a mathematical representation, and for each square here, for each random variable, we have a measurable space. Each random variable has its probabilities, its algebra, but also because of, for each row of this matrix, we have a joint probability distribution, because they form a context. We also have a measured space for each row. So this sigma algebra here that we will take as Boolean will be very important. Now I want to raise the question, the attention on a question, which is, what are we going to do with experiments that appear in different contexts? For example, in quantum mechanics, the same experiment can appear in 2 different contexts, but this guy here on the left is not prepared. If this one is actual, the other one is counterfactual. That's what happens in quantum mechanics. So in general, what are we going to do with regard to identity of these experiments? And also the random variables. Should we identify those random variables? So some people say, well, they are simply identical. They're just the same, and they are mathematically the same random variable. But it has been argued that they are different random variables. And that's a very reasonable assumption in some areas of research, because these random variables might have different probabilities distribution even. And so they appear in different contexts. So some people propose that they are different. But in physics, it seems to us that there's something else. So indeed, we cannot say that they are just equal, but we cannot say that they are different, because they are completely alike. And that is why with Acacio de Barros and Destu Krause, we propose to consider them as indistinguishable. So you have a philosophical debate already here. So you can consider them as equal, indistinguishable, or different. These are 3 different positions that seem very naive, but at the end of the day, they turn out to be essential in the mathematical constructions that you can make. So the idea is that we have a collection of classical probabilities, one for each context. So each experiment has its own Boolean algebra, And this Boolean algebra is a sub-algebra of a bigger Boolean algebra that represents the context. And you have a measure from the context, that is the joint probability, and a probability measure for the experiment. But if nothing about quantum mechanics were known, if you don't know about quantum probabilities, Hilbert spaces, or nothing, you can consider a state as a collection of classical probabilities. And a classical statistician could work without quantum mechanics. There are a lot of things that can be done, and perhaps everything can be done. I'm quite sure that you might not know nothing about quantum, the Hilbert space, and nothing. And if I give you the collection of all classical probabilities associated to the context, you will be able to speak about contextuality and so on. But we know in physics, we are interested in continuing the story because we know that things are intertwined. These algebras can be considered as subalgebras of a global object, which is the lattice of projection operators of the Hilbert space, or equivalently the lattice of closed subspaces. And so this object here gathers all these Boolean algebras of the context in a single object, and you can define a global measure, which is non-Kolmogorovian, into the interval 0, 1 that makes this whole diagram commute. And there is more. You can also embed all of this in a ring of operators, for example, self-adjoint operators acting on the Hilbert space, and define a state as a density operator. Due to the Glisson's theorem, we know that this state is unique. There is a unique representation of this. So we have a classic, we can consider a quantum state as a collection of classical probability spaces, but there is much more structure. And we are interested in seeing how this structure appears or emerges. So there are, as far as I know, at least two ways of describing global states. One alternative is keep using Boolean algebras here. I mean, build a global Boolean algebra, but allow this global measure to be negative. And the second alternative is the usual one in quantum physics, which paste the Boolean algebras and end up in a global non-Boolean structure, which is a non-distributed lattice, and define states as usual in quantum logical approaches. This could be, well, you can use orthomodular lattices or partial Boolean algebras. It depends on the taste and the aims of the user. But this is the problem. I want to make some comments about these two alternatives. First, I will speak about the joint work with Acacio de Barros. This is published in this paper. If you want to see the details, you can go. So we were wondering about possible connections between the notion of indistinguishability and negative probabilities. So we realized that we needed a general definition of negative probability, but that was based on measure theory, as in Kolmogorov's actions, and that it is independent of any Hilbert space structure. And we wonder about how to incorporate the notion of context from the very beginning in such a negative measure theoretical probability approach. Of course, there are other approaches to this and that satisfy some of these conditions. But I want to talk to you about this today. So the first starting point could be, instead of having a measurable space, consider simply a sign measurable space, which is completely equal to a measurable space, but you allow this measure here to take negative values. But the problem with this is that you don't have a notion of context in this setting yet. So how can we define contexts in this sign measure spaces setting? What we did is to consider the notion of extended random variable, which is very similar to that of random variable. So it is a measurable function, but now considered in a measurable space. So the pre-image of every Borel set, suppose that it takes values on the real line, the pre-image of every Borel set will be a signed measurable subset of the sigma algebra. So now, with this definition at hand, we can consider a family of sign probability models, of sign measurable spaces, which have all the same common Boolean algebra and outcome set, and consider a collection of extended random variables defined in that setting. So a subset of this random, a proper subset of these random variables will be a context if there exists a sub-sigma algebra of the global sigma algebra, satisfying that when the measure, the global measure is restricted to the elements of the sub-sigma algebra, one obtains a classical probability space in the sense of Kolmogorov. So to put an example here, in the blue box, you can see the global Boolean algebra and the measure that might take negative values. But when you restrict this measure to, for example, the sub-sigma algebra or sub-Boolean algebra associated to the red context, you obtain a classical probability space. And the same for the green and the same for the black context. But in order to build, for example, in this example, the X, Y, and Z three dichotomic random variables scenario, if we want to build actually the global Boolean algebra, we notice that an identification principle is operating. Because in order to say that the random variables, in order to justify that the random variables have the same probability, we say that they are indistinguishable. Because otherwise, we cannot make this compatible and satisfy the single condition. Well, this is signal by construction, by the very construction. So, what are the features of this definition? Well, it can be used to define contextuality in a way which is familiar to physicists. So ask about how negative is your global state or how classical is your state and so on. You can play that game with this. It includes previous examples of no-signal models as particular cases. Also, it is important to remark that the negative probabilities never appear in experiments because only concrete contexts represent what actually happens in a laboratory. And also it is possible to define an entropic measure in the usual way of defining Shannon entropy on each context and afterwards take the infinite. This will give you a very natural definition so the first example that I put of constructing a global Boolean algebra that contains all the algebras of the context as subalgebras is using negative probabilities. The second possibility is related, remember, we have for each row of the collection of random variables, we have the Boolean algebra. So there are two options here. Should we identify the Boolean algebra over the columns, the Boolean algebras, or not? There are two mathematical possibilities here. If we don't identify, there is a very simple solution at hand to get a global object. So, because given a family of Boolean algebras whose intersections are simply given by the top and bottom elements, each time they are different, it is possible to create a global object, which is the horizontal pasting of these Boolean algebras. And this is an orthomodular lattice, as in quantum mechanics. And this is valid for any family of Boolean algebras that satisfy this condition. And you have this global object, this global state here might be signaling. Why? Because this pasting of Boolean algebras just create copies for when they are repeated, they are just copied and not identified. So you can assign any probability to each element and you will not enter into contradiction. But this pasting loses information about the intertwining of the Boolean algebras. So another interesting possibility is consider that in physics, the no signal condition suggests that we should identify the random variables of the columns because they have the same content and the same probability distribution. So we notice again that an indistinguishability principle seems to be operating here. Given that they are physically indistinguishable, then we have an identification rule for intertwining the Boolean algebras. Now, it is true that the lattice of projection operators of the Hilbert space can be described actually as a pasted family of its maximal Boolean algebras. Remember that each maximal Boolean algebra represents a measurement context, a complete set of commuting observables. So, posing the problem in this way, we think it's useful because it allows you to use standard results of algebra, because mathematicians have been gluing orthomodular cosets and Boolean algebras for years. So we think that this is a very interesting point of view. And also it allows to come into play group theoretical conditions, because we noticed that in quantum mechanics, all maximal Boolean subalgebras are isomorphic, and everything is generating by the action of a continuous group. That's a very peculiar feature of a family of random variables. It will not happen if you pick a system at random in nature. It only happens in very specific physical systems, as in quantum theory or in quantum field theory and so on. So these are some standard references on, if you are interested in see how in mathematics people paste things, especially these structures that are interesting for quantum theory. Now I want to comment something about the joint work with a mathematician who's called Cesar from Argentina. These are some papers that we've been working. We are moving very slow in this because perhaps the mathematics is too hard for us, but we've been making progress. So I want to pose the problem in a different way. All what I said is related to this. People always questions about why Hilbert spaces. So let me quote Hilbert, von Neumann, and Nordin. This is taken from one of the seminal papers that later gave birth to the standard quantum formalism. So they say, regarding to the previous axiomatizations of probability of Pascual-Jordan and others, they say one imposes certain physical requirements on these probabilities, which are suggested by earlier experience and developments, and the satisfaction of which calls for certain relations between the probabilities. Then, secondly, one searches for a simple analytical apparatus in which quantities occur that satisfy these relations exactly. Well, at the end of the day, the simple analytical apparatus was the Hilbert space. So you can actually see the role played here by the Hilbert space. The Hilbert space is just a representation of something which is primitive, that are the probabilities. And you figure out by studying phenomena how these probabilities are, and then you try to find a representation. There's nothing special about it. So I'm, of course, super simplifying the story. You can, I strongly suggest you, if you are interested in this, to take a look at this paper by Duncan and Jensen, which is a historical paper that has a lot of conceptual considerations about this problem. So then, while most of the strategies focus on looking for actions to justify Hilbert spaces, we think that it is also interesting to pose the problem in a different way. Suppose that we start by assuming that systems are described by a global algebraic structure. These structures might be non-Boolean, as I showed you in the previous examples. So we try to understand how a possibly non-abelian ring, a ring that resembles the rings of operators that we use in quantum theory, emerges out of this minimal operational structure. I call it minimal because it comes from experiments and a minimal mathematical apparatus, that is to represent probabilistic experiments using measure theory in the usual way. So we want to go this way. Once that you buy that there will be a global object here, then you try to find a ring of operators that resembles quantum theory. So what is interesting about, for example, the category of orthomodular lattices is that you can define a compatibility relation that depends only on the lattice structure, does not rely on any Hilbert space consideration. It's primitive, so to say. Also, you can consider partial Boolean algebras, but we restrict to orthomodular lattices. So what we do is to form the free algebra of all possible linear combinations of elements of the algebra. And what we do is to create an ideal that identifies, allows us to identify certain elements. So we create an object with this sort of universally non-commutative algebra that has the following properties. In this object, there is a copy of the elements of the lattice. I mean, the elements of the lattice are the events of the physical theory that we are considering, in such a way that they behave in a similar way to projection operators. They are the idempotent elements, using this notion of compatibility. And then out of them, we can build what one might call the Hermitian operators or the self adjoint elements of this ring. So what we have is a lattice that comes from an empirical structure and build a sort of ring of operators. So we think that this approach is promising because if pursued successfully, will show that after all, operator algebras might not be so strange because they arise naturally each time that you have a family of random variables. So that will be another way to justify why Hilbert space is so important, or at least give a motivation to it. So understanding contextuality to a great extent is related to understanding how contexts are intertwined. And then in this talk, we ask about how global states and even algebras emerge. Then we find that the identification of random variables among different contexts seems to play a key role in their genesis. So there's a sort of indistinguishable principle playing. So we have discussed the general features of two alternatives, Boolean algebras plus negative probabilities and non-Boolean algebras plus generalized states. So these are some papers, and this is the end. Thanks for attention.
I have one question.
Yes.
When we deal with orthogonal lattices and measures on them, so okay, if we have an embedding of the orthogonal lattice to a Boolean algebra, and we try to extend a measure from an orthogonal lattice to that Boolean algebra, this may be impossible. Sometimes this can be solved by extending it to a signed measure, as you mentioned, so that this solves some problems using, in some sense, negative probabilities inside this model. But this is possible only sometimes. So we know that there are many situations when this cannot be, when a measure on an orthogonal lattice cannot be extended even to a signed measure. Even under rather restrictive conditions, this is impossible very often.
Thanks,
so
Mirko.
This solves just a part of the cases.
Thanks, Mirko. It is, I think that there are a lot of things that can be said about how to connect negative probabilities in this setting, and the story, of course, is not ended. I will check on what you have just said in the papers. It's certainly a direction that we have to look at more carefully. The problem, I think, is that when you have an arbitrary collection of random variables, it is very unlikely, I think, to find a global object that has some structure. So I think that only under very special circumstances you can, for example, paste orthomodular posets and get an orthomodular lattices, or Boolean algebras and get an orthomodular lattice, and so on. So thanks for pointing the relevance of the negative probabilities. I will check.
Yes, but
Okay.
well, maybe it's a very quick question, but when you mention this principle of indistinguishability, would you say it is related somehow with the Specken's approach to contextuality when he cites the Leibniz principle of identity of indiscernibles?
Well, no, I think it does not. That's an interesting question, because I think we are going the other way around. I think that Speckens uses the principle of identity of indiscernibles as true. He says, well, things that cannot be distinguished should be identical. But we are going the other way around. Let me put this slide here, because I think it's a subtle point. Because this idea of indiscernibility that we are dealing comes from non-reflexive logics. with that had to do with violations of the principle of Leibniz. So no, we go the other way around. I think we are saying that these two guys here are truly indiscernible, in the sense that you will not be able, by any operational means, to discern if you are whether you are in this context or this other context, if you're locally measuring here. But notwithstanding, there are still two of them. So there are two things here, not one. The principle of Leibniz says if you have two indiscernible things where there are no two, there are just one, they're equal. So we are going the other way around. We're saying we have two truly indiscernible things, and this indiscernibility, so in that way we go in the direction of saying they are not the same, but at the same time that allows us to say, well, the fact that they are indistinguishable allows us to justify why they must have the same probability, the same everything, so you cannot distinguish by any experiment whatsoever, and then to make a mathematical identification at the level of basing of or whatever you're going to do. I think that should answer your question.
Okay, thank you.
It's a question I got in late to your talk. I hope I didn't miss something essential. But it seems to me that if you simply use the Hilbert space, I'm a physicist, and simply identify physical properties with the projectors, everything works fine. I mean, to use the diagram, you just add up. In different contexts, well, you're using the same projector. It means the same thing, and you know, this gets around Bell's original idea was if you measure something well, the outcome may depend on the context. But I've shown that is incorrect. That the you know, the measurement result, assuming the usual simple projective measurement model, doesn't depend on the context, and this is simply Hilbert space projectors.
Well, yes, thanks, Robert. I think that point is important because that's why perhaps I didn't explain it well, but that's what I think I'm trying to say in this slide. So in quantum theory, this diagram closes perfectly. So the diagram fits perfectly. But what I wanted to do is to call the attention on how magical this is and how strange this is, because you are out of all possible collections of Boolean algebras, you know that they can be pasted in a global object that is not any kind of global object. It's a very specific mathematical structure, which is an orthomodular lattice, modular in the finite dimensional case, with modular in the infinite dimensional case. And at the same time, you know that this lattice, the elements of this lattice, can be considered as operators acting on a ring of operators, which is what you call the Hilbert space formalism. That's the essence of it. So the question will be, give me an arbitrary collection of random variables. Is it possible to repeat the feat of quantum mechanics? How likely is that? What are the, because we know that because this pasting is not as the horizontal pasting. It's not just that the algebras do not touch each other, as all the work in contextuality shows, so for example, the work of Adam or the work of Eddie, but there are things in common. And they are, the Boolean algebras are intertwined in a very complicated way. And this is something that I think is very interesting for physics, and we need to know. And I think that we don't know, and I want to know. And that's the motivating idea of our humble research program. I mean, again, we are moving really slow, I think, with this, but I think we are making progress.
So what is it you want to know?
Well, for example, yeah, a concrete example. Suppose that I have an arbitrary family of random variables, arbitrary. Now I want to ask, what conditions should I impose on that arbitrary family in order to obtain a quantum structure like the orthomodular lattice of quantum mechanics. I want to understand how these contexts are intertwined. You might even the Kochen-Specker theorem as a first approach of how this, as a first glimpse. We are looking, I think, at the iceberg peak, but there's a lot of structure that we really don't know, and there's a lot of work to justify why Hilbert spaces are so, or seem to be so special in nature.
Thank you. I mean, for a physicist, it's simply, you know, you use math that agrees with the world, as in special relativity or general relativity, and the world is such that Hilbert space works. You know, I don't deny that there are other interesting questions, but that's sort of my perspective.
Yeah, yeah.